Hi, welcome to the channel. My name is Wallace. In this video, we continue with electricity in netted engineering science. In the previous video, we discussed what electricity is. We looked at voltage, we looked at current, we also discussed resistance and also how important Ohm's law is. We also then looked at the resistance of a conductor and how different factors affect the resistance of a conductor, and we did a calculation. So if you have not seen the video, please check it out in the link. In this video, we'll be continuing, like I said, we'll just discuss a few things and trying to cement what we have already started. Electricity is a very wide topic, so it is not something that we can just digest in one video. So I'll try by all means to also make this a short video and probably make follow-up videos. In the previous lesson, we discussed current, voltage and resistance, and that all of these three, they relate by a law called Ohm's law. It is very important that we understand Ohm's law and we know how to state Ohm's law. I cannot overemphasize the importance of Ohm's law. So we said current, the unit for current is amps, we are using A. The unit for voltage is volts, we are using V, and the unit for resistance is ohms, we are using that Greek symbol. And all of these, they relate using Ohm's law. With current, the instrument used to measure current is the ammeter. So this is the instrument that we use to measure current. Whenever we see in a circuit there is an ammeter, which will be represented when they draw a circuit for us, they will do that. Then just know that this is an ammeter and it is measuring current. They might not say what is the current reading on ammeter, they'll just say what is the reading on that instrument. Knowing that it is an ammeter, then it is reading current. An ammeter will always be connected in series. We'll discuss what series and parallel connections are, but an ammeter, current should pass through it, then it reads the current that is flowing at that particular point in a circuit. Then a voltmeter measures voltage. Voltmeter measures voltage. They'll also draw with a V like that. So it is very easy to remember those. As long as you see V, that's a voltmeter. You see A, that's an ammeter. A voltmeter measures voltage. They'll just ask you what is the reading on that instrument. If you see it's a V, then it is reading voltage, and you give your answer in volts, whatever your calculations might be. Then a voltmeter should always be connected across a component. So let's say, for example, a voltmeter is reading across a bulb. Let's say this is our bulb, our light bulb. A voltmeter will go across. It will measure from that point to that point. Remember what we said? Voltage is the influence that is causing the electrons to move. The electrons move along, so the voltage will be how much influence is on this side compared to that side. So for resistance, resistance is measured in ohms, and it's the ohmmeter. So these words are very easy to remember. An ohmmeter measures resistance. With an ohmmeter, we shall not see it connected in a circuit. It is just measured separate. But for an ammeter, we might see it. For a voltmeter, we might see it, and the voltmeter is connected like that. If it is an ammeter, like I said, it will be in a series. This is our light bulb, and so on. So the other thing that I want us to take note of is under voltage. Under voltage, you have what is called potential difference. They will abbreviate this to say PD. Potential difference is a voltage. The unit for potential difference is still voltage. So keep in mind, I'm just talking about voltage. And there is also what is called electromotive force. electromotive force, they'll abbreviate this to be EMF. Okay, also electromotive force, the unit is still volts. Both of these, potential difference, electromotive force, EMF, they are all voltages. So remember, like we defined electricity, we said it's electrons moving. We can even look at this, it is almost electrons, there is motive, there is a force. I was trying to avoid that word force for the voltage, the influence that is causing the electrons to move, but you can as well just think of it as a force, which is a voltage that is causing the electrons to move. So both of these, potential difference and electromotive force, they are voltages. Now, what is the difference between them? Potential difference is the voltage across a component, like I gave earlier, where we said if we have a light bulb, this is just my drawing of a light bulb just to make it a bit clearer, and you use a voltmeter. Remember a voltmeter? Voltmeter measures voltage, and we said a voltmeter you connect across. So this is our voltmeter. It compares the voltage on this side and on that side, then it gives you the difference in terms of how much influence or how much energy is on this side compared to the amount of influence causing the electrons to move on the other side. So it gives you the difference between 2 points. That's why it is called a difference. It gives you the difference in the potential on this side and the potential on that side, then it gives you a difference. So potential difference is basically, we can look at it as the voltage drop across a component. So if this light bulb is using up electricity, voltage is coming at a certain amount of influence, this light bulb uses it, it decreases that voltage. How much the light bulb is taking up, the amount of voltage it is using up as it is connected in the circuit. So that is the potential difference across that component. So it's just, potential difference is the voltage drop across an electrical component. I hope it makes sense. Then when it comes to electromotive force, this is the voltage, and I'm trying to make this as simple as I can for us to understand. Voltage from a source. Okay, so this is voltage from a source. We know that electricity has to have a source. If we are looking at a circuit, probably a source would be a cell or a battery. Okay, so the voltage from the source, the sources being the cell or a battery, or it could be a generator, it could be it could be anything, as long as it is producing that voltage that is coming from a source of electricity, that is regarded as EMF. The electromotive force, the energy at which the electrons are being moved or are being pushed out of a battery or a cell. So that is EMF. So EMF, you find it across sources. Potential difference, you find it across components that are using up the voltage. However, a battery can also have potential difference if the battery has got internal resistance. You might find that the EMF of a battery, let's say, is 12 volts, but due to internal resistance inside that battery or that cell, you find that at the end the battery is only giving out maybe 11.8 volts. The other 0.2 volts has been lost due to the internal resistance. So the resistance is taking up that 0.2 volts from our EMF. So this will be our EMF from the battery. Then the potential difference will be 11.8. This is just an example for us to understand that EMF and PD can exist in a battery when there is internal resistance, but EMF cannot be found across components like resistors or light bulbs. It can only be found, potential difference can only be found at light bulbs. We cannot find EMF at such. Only EMF is only found at the source. I hope that clears the idea. But all of these, they are all in volts, so do not confuse these two. So whether you're calculating for EMF or you're calculating for potential difference, Ohm's law still applies. Ohm's law states that the current flowing in a circuit is directly proportional to the applied voltage and inversely proportional to the resistance. It can be potential difference or it can be EMF, but still this applies, and what we are looking at is that voltage. Whether it is EMF, whether it is potential difference, it still remains current is directly proportional to the voltage and inversely proportional to the resistance. So you may find this same Ohm's law formula written in different versions, PD over R. It might even be written as EMF over R. So this is still the same thing, still Ohm's law. EMF, we know it's a voltage. Potential difference, we know it's also a voltage. So no need to be afraid of that. We still around Ohm's law, and like I said, electricity, our key fundamentals is Ohm's law. Here's another thing that we need to keep in mind as we do electricity is that there are components and then there are symbols that they use for drawing. For us, just doing engineering science, we won't go into all the many symbols that they are, but I just want us to know that in case we are looking at a battery, how will a battery be represented? They will represent a battery like this. So now this is a battery with 3 cells. A cell is just a component that is having one positive and a negative. So this is a battery, this is a cell. The longer part being a positive, the shorter side being a negative. So also on that one, the positive and the negative. That is a battery and a cell. Then the other component that we will come across is a resistor. We will discuss resistors just now. A resistor, they will draw a resistor like this. In other older versions, they will write a resistor like that. Well, there are many other symbols, many other forms of resistors, variable resistors, you have light dependent resistors and so on. But we are not doing electrical engineering. We'll leave those symbols to the other guys. And then also, like I mentioned, the voltmeter, we already saw the symbol they use to just be with a V inside. An ammeter, it will be with the letter A inside there. Okay, maybe a switch. Okay, so this is an open switch, it is off. Then a switch that is closed, to have something like that, that is a closed switch. So this one is off, this one is on. Electricity is passing through the switch, and this one electricity is not passing through that. So I think basically these are a few that we will come across, but there are many symbols. We'll leave that to those that are doing electrical or electronics engineering. And also very important is that all the components that you'll be calculating the voltage across, maybe a light bulb, or voltage across maybe a loudspeaker and so on, all the components, all those components that use up electricity, they are resistive in their nature. So you'll be treating all components just the same way as you would treat a resistor. And we remember that a resistor offers what is called resistance, and resistance is inversely proportional to Ohm's law. So we will always go back to our Ohm's law. So whatever component, every component that we might use, they are resistive in their nature. We find their resistance, then we apply in Ohm's law. As long as a component uses electricity, it is resistive in its nature, and it will oppose the current, and thereby in the process of opposing the current, it is actually doing its function and giving us whatever we might need from that component. So a light bulb, it is resistive in its nature. By resisting, it gives out light, it gives out heat and light at the same time. And every component that is resistive in its nature, it will have a potential difference, how much voltage it is dropping. So we can be able to calculate how much voltage drop across the components, using the same formula, current times resistance. So this will be the voltage drop across that component if we know the amount of current that is going across that component. Okay, lastly in this video, what I want us to take note of is the types of connections. This is very important under electricity, and do not attempt any question if you cannot identify the type of connection of that circuit. So there are basically three types of connections, but I'll emphasize on the first two. So we have a series connection, we have a parallel connection, and then you have a combination of these two, the series and the parallel. When they are combined, you have what is called a parallel series or a series parallel connection. Okay, so we are not going to emphasize much on this one. Our emphasis should be on understanding what happens in a series and what is happening in a parallel connection. Do not answer any question that you do not know whether it is a series connection or it's a parallel connection, because with electricity, everything now will start depending on how the components are connected to each other. So let's say, for example, if I've got two resistors, and by the way, a resistor, this is what we said is connected. A resistor offers resistance, so its units will be in ohms. So let's say we have a 20 ohm resistor, and on this one we have, for easy calculation, I'll say we have 10 ohms. These are series resistors. How we calculate for the total resistance of this is different if we had the two resistors connected in a parallel connection like this. So let's say this is still our 20 ohm resistor, this is still our 10 ohm resistor, and all of them are connected to the same supply voltage. I'll give our supply voltage 12 volts. We also connect this to the same 12 volts. Okay, so they are the same components in these two circuits: 20 ohms, 10 ohms, 12 volts, 20 ohms, 10 ohms, 12 volts. They are doing different things because the circuits are connected in different formats or different types of connections. So number one, we'll focus on this one for now. Number one, the total resistance RT in this series connection will just be your resistor 1 plus your resistor 2. If we have other resistors connected in series, we'll continue adding as long as the connection is what? It's a series. So it doesn't matter whether we have one resistor here, another resistor there, it is still a series connection. It is not about the corner that we have there, but it's how one component is connected to the other. So in this case, we'll have 20 plus 10, our total resistance is 30 ohms. Okay, so with a series circuit, the resistance, the total resistance is a sum of all the resistors. As long as they are connected in series, the total resistance is a sum. Now, obviously, according to Ohm's law, the current that will flow in this circuit, voltage over resistance, our voltage is 12 volts over our 30 ohms, we get 0.4 amps. So in this circuit, the current that will flow, remember this long one is a positive, the other one is a negative. Electricity, conventional electricity, flows from positive, goes all the way and back to the cell, from positive to negative. Alright, so in this circuit, what we have is 0.4 amps flowing in this circuit. It will pass through this first resistor, come out, it will still be 0.4 amps, pass through resistor, come out, it will still be 0.4 amps, until it returns to the battery at 0.4 amps. So in this circuit, what we can also note that the current is the same at any point in a circuit. If we connect an ammeter here, the ammeter reading will be 0.4. Whether we connect it here, our ammeter will still be 0.4. In a series, current remains the same. Okay, so please note that in a series, the current remains the same. It will always be the same at any particular point in this circuit. However, with this series circuit, each component will have a different voltage drop. And what we mean is that if we want voltage across the 20 ohm resistor, according to Ohm's law, voltage that will drop across each component is the current times the resistance. Now remember, the current is the same throughout the circuit. We have 0.4 times our 20, then we get our 8 volts. So this resistor will have a voltage drop of 8 volts. The voltage drop across our 10 ohm resistor will be the current which is the same, times the resistance of that. Our current is 0.4, we multiply by 10, our voltage drop is 4 volts. Alright, so in a series, the voltage drop across each component is unique depending on the resistance. The big resistor gets a big share. So a series circuit, it shares the voltage that is being produced. The components, they are all sharing this depending on their sizes. The big resistor gets 8, the smaller guy gets 10, depending on their sizes. If they were all of the same size, they will share this 12 equally. A series circuit is also known as a voltage divider circuit. It is sharing the voltage. Alright, then you go into other laws like the Kirchhoff's laws and so on, but for our engineering science, I think this is enough on the circuit. Keep in mind, the total resistance is the sum of the resistors, the current remains the same, and also the voltage drop across each component is dependent on the resistance. It is not the same. So if we add the sum of this is a potential difference 8 and the potential difference of 4, if we add this to it will give us our total EMF. So in a series, our EMF and our PDs, these are our PDs, if you add up, our EMF is equals to the sum of the potential differences in a closed circuit or in a series. Now when we go to a parallel connection, in order for us to know the current that the battery will send out, we first need to know the total of the resistance. According to Ohm's law, current flowing is dependent on the voltage and inversely proportional to the resistance, or in this case to the sum of the resistance. So with a parallel connection, in order for us to get the total resistance, it will be an inverse. I'll use P, an inverse of RP, and everything will be resistor 1 plus 1 of resistor 2 plus 1 of resistor so and so. As long as they are connected in parallel, it should be an inverse. So in this case, we shall say 1 of 20 plus 1 of 10. Okay, we quickly work our calculator. We get 3 of 20. Now, do not give your answer in decimals at this point, because we are not interested in the inverse of the resistance, but we are interested in just the resistance, which is our RP, this guy. So at this point, you make RP the subject of the formula, you cross multiply. But basically what I like to do, just to save time and also do a bit of some shortcuts, is that I'll just flip these ones. If we flip RP of 1, we flip them up, we also flip on the other side, which becomes 20 of 3. Though this is not a mathematical explanation to it, but it does the job. So any number divided by 1 is the number itself. So what we have is just RP 20 over 3, and now we can calculate for that and leave that in a decimal. So our resistance is 6.667 ohms. Okay, so from these 3 resistors, I hope you can see my 6.667 ohms. So from these 2 resistors, our total resistance is 6.667 ohms. And also, this is important to note that in a parallel circuit, we have, in this example, we have 10 ohms, we have a 20 ohms. Our total resistance is smaller than any of these 2. This one is a 20, this one is a 10, but our total resistance is a 6. If we get any number above the smallest guy, 10, then somewhere in our calculations we made some error and we need to recheck that. So every time you have parallel resistors, just look at the smallest guy and know in your mind that your answer should be less than that smaller resistance. So our total resistance is 6.667 ohms. So then, to know how much current will be sent from our battery, our current using Ohm's law, voltage over resistance. So our voltage is 12, 6.667. Our current is 1.8 amps. It is 1.799, but we'll round off to 1.8 amps. So our battery will send out 1.8 amps. This 1.8 amps, it flows and reaches that point, and we shall call that a junction. Now what happens is that when it reaches this junction, this 1.8 amps, some of it will split, go this side, and some of this same 1.8 will go to the other side. So in a parallel circuit, current is split, and it is splitting depending on how much resistance. Electricity is always trying to find the easiest way. So out of this 1.8, we will know that where there is less resistance, more of this 1.8 will flow through there and less will flow on this one with the high resistance. Current will always flow easy where there is less resistance. And when these two currents come back and meet at that point, whatever current went through this side, it will add up and it will add up to that, and we'll have the same 1.8 amps returning to our battery. Okay, so it's very important to know that current splits in a parallel circuit. But then how do we know how much current splits? We shall go back to our Ohm's law, and then the other thing that we shall say is that the voltage across a parallel connection remains the same. The voltage across the parallel connection will remain the same. So the voltage across this 10 ohm resistor is 12 volts because it is connected straight parallel to this 12 volts. The voltage across this 20 is still 12 volts. Okay, so in this case, all of these, they are having 12 volts. However, let me also emphasize this. If our circuit was like this, okay, so now these are 3 resistors. I'll say 20 ohms, 10 ohms, I'll give 5 ohms there, and then we have our our 12 volts. Okay, in this case, these two have a voltage that is the same, but it is not this 12 volts because they are not the only components in this circuit. There is also this 5 ohms. So we'll deal with these ones at a later stage. But for this circuit, it is 20 ohms in parallel to the 10 ohms also in parallel to our voltage. So they will share the same voltage. That is very important to know. In this case, 20 and 10 have the same voltage, the same like we discussed, but that voltage is not 12 volts. Alright, then how much current is flowing through resistor 20? Current is equals to voltage over resistance. We know our voltage is the same, so the only thing that is changing is the resistance over 20. So we are calculating for this 20 ohm resistor. 20 into that, we get 0 amps. Okay, we go to this other one. Current over the 10 ohm resistor is which is voltage V over R. Our V, we already know it's 12 over 10. This gives us 1.2 amps. Okay, so from this 1.2 amps goes on this side, 0.6 amps goes across this one. The big guy now, it is opposing too much, so only a little amount of current will go through there. On the 10 ohms, the smaller guy, a lot of current will pass through there, and it is that all current is coming from there. When these two currents 0.6, 1.2, they meet up there, they will add up and give us the total of 1.8 amps. The same amount that left the battery is still the same amount of current that returns to the battery. Alright, so in conclusion, what we can say is that a parallel circuit is a current dividing circuit. Current always splits at the junction, and now that will now give us laws like Kirchhoff's current law applying to this, where now we can say current flowing to a junction, the sum of current to this junction is equals to the sum of current flowing away from that junction. So if we have current of 1.8, you look at the arrows, current always has direction. 1.8 flowing to this junction, and we look at how much currents are flowing away from this junction. Those arrows, we have 1.2 and 0.6. The sum of those ones flowing away should be equals to the sum of the current flowing to the junction. Well, in order not to make this video too long, we'll understand this type of connection, the series parallel or the parallel series connection, when we do a question that involves calculating for different components that they will ask us in our examination. This question reads as follows. Two resistors, 6 ohms and 11 ohms are connected in parallel. This parallel combination is now further connected to 3 ohm resistor in series. Determine the resistance of the parallel connection. Then the next question, the total resistance. Then the next question, the current through the 6 ohm resistor. Alright, so I'll just do a sketch of how this circuit looks like.
And we have 11 ohms. These two parallel resistors are now connected to a 3 ohm resistor.
The first question says determine the resistance of the parallel. So our first question, resistance. Which is this two. Remember what we said? For the parallel resistance, it will be 1 over resistor 1, resistor 2, and so on. One over 6 plus 1 over 11. Then like I said, you just flip them over. Then after we calculate this, that gives us our answer. This gives me 3.882 ohms. Please follow through with the calculations. Sometimes I make mistakes. Then the next question says the total resistance. So our total resistance is now a combination. These two combined gives us 3.882 plus this one. So our total resistance will just be the parallel resistance plus our series resistance there, the 3 ohms. So we'll say 3.882 plus 3 gives us 6.882 ohms. That is our total resistance. They give us all the marks for that. Our next question says calculate the current through the 6 ohm resistor when the circuit is connected to 50 volts supply. The last question is asking for the current passing through the 6 ohm resistor. How much current will go there? So the first thing, we have to know how much current will leave this battery. The current that leaves the battery, we can calculate it by knowing how much current it will send out using the total resistance. So current that leaves the battery is the voltage divided by the resistance. Our voltage is 50 volts. Our resistance is 6.882. Our current that leaves the battery is 7.265 amps. So 7.265 amps leaves our battery. It reaches this point, it splits. Some of this, more of this will go through our 6 ohm resistor, a lesser amount will go through our 11. When they meet there, it will be the same. Should they have asked us how much current is passing through this 3 ohm resistor, it's still the same. So we're looking at this. So our next step is to find how much voltage is dropping across these two. Remember what we said? Voltage across the parallel is the same, but now this is a parallel with a series. So the voltage drop across the 6 and the 11 is not 50, but it is a certain amount which is the same, and we will get that amount by doing this. So remember when we combine these two, we got our one resistor which was, okay, this 3 ohms is that 3 ohms. The combination of these two is 3.882 ohms. When we combine these two, we got 3.882 ohms. So these two resistors and these three, they are exactly the same, because when we combine this, they give us 6.882. These two give us 3.882. All right, and the current that is going through them is 7.265 amps. So the voltage across, this is a parallel, your parallel resistors. These are your parallel resistors. So the voltage across your parallel combination is your current times your parallel resistors. Our current is 7.265. Our resistors is 3.882, and this gives us 28.20, we round off 3 volts. Okay, so the voltage across this, the voltage across this guy is 28.203. The voltage across this, so it is this 28.203 is across the parallel combination. So now that we know the parallel combination, the voltage around or across these two, which is 28.203, then we can calculate how much current there is using this 28. Current across our 6 ohm resistor is the voltage over our resistor Now this voltage, not the 50, will be this voltage across the parallel, or the parallel voltage if you want. We'll say 2803 divided by our 6 ohm resistor, which is this, gives us 4.7005. We round off that 5. This is a current, amps. Okay, so 7.265 is moving from our battery. It reaches here. Out of this 7.265, 4.701 amps goes this side. The remaining goes the other side. If you want, you can calculate, but they have not asked us for that. Current across the 11 ohm resistor to be still be 28,203 over your 11. You get 2.56. We round off that amps. Okay, so on this side we have 4.701. On this side we have 2.564 amps flowing through there. When we add these two currents, if we add these two currents, they should give us something close to this amount. If we add these two currents, they should give us something that goes close to that. Okay, and the reason is that after we add these two, it gives us this amount, is because that current is splitting. Some of this current goes that side, some of this current goes the other side. So I think that gives you an understanding of basic electricity questions that you might come across